Is Quicksort really better? Let us analyze the running time of it. So we first talk about the worst case, which is the normal way to analyze an algorithm. We see that actually in the worst case, we cannot avoid any comparison. For instance, suppose that when we are picking a certain p as the pivot, we are so unlucky that after this partitioning step, after this separation step, we find that all the numbers are in S large. So in such a case, so we are not avoiding any comparison because there is nothing in S small at all. Now to see this is really a bad case, so let us use Tn to denote the worst case running time for sorting n numbers with quicksort. Then if every time when we are doing this pivot and separation step, we find that all the numbers are in a certain group, then T of n can be expressed as n, which is the time to compare the pivot with all the other items, plus T of n minus 1, because we are now having a subproblem which needs to handle the remaining n minus 1 items in the same group. So Tn will be equal to n plus Tn minus 1. Let's say this is a certain kind of a bad case. Now if we solve this, we will find that Tn is equal to n plus n minus 1 plus n minus 2 and so on and so forth, and it is equal to theta of n squared. So in the worst case, the running time of quicksort is n squared. But how about the best case? Okay, so normally we will not analyze the best case of an algorithm, but for here, let us see what could be the best case for quicksort. Now the best case for quicksort is the situation where we can avoid the most number of comparisons. So when can we do so? When can we avoid the most number of comparisons? It is when S small and S large are roughly the same size. So let's say half of them are in S small, half of them are in S large. So in that case, we maximize the total number of pairwise comparison between them. So in that case, we can avoid all these pairwise comparison between them. So here we let T star n to denote the best case running time for sorting n numbers with quicksort. Then T star n can be expressed as n, which is the time to do the comparison of the pivot with all the other numbers, plus this is the subproblem of size n over 2, and it takes T star of n over 2 to sort the S small, and it takes T star of n over 2 to sort the S large. Now, this recurrence relation looks super familiar. So this is actually the same as what we see for merge sort. So by solving this recurrence, we will find that T of n is equal to theta of n log n. So we can also apply the master theorem to solve this. So this is of theta of n log n. So we can see that there is a huge difference between the worst case and the best case. Worst case is n squared, while the best case is n log n. But in fact, we do not need the best case to get theta of n log n. So for instance, if most of the time the partition of S small and S large are not too skewed, the running time could still be good. For instance, let's say S small is like 1/3 of all the items, S large is 2/3 of all the items. So in that case, we can still bound it to be n log n. And indeed, the average running time of quicksort is actually theta of n log n. But then we are not going to analyze this because it is out of the scope of this class. But if you are interested, you may check the textbook. So the textbook has the analysis of the average running time of quicksort. And also, there is a stronger result. So here, the pivot, we didn't tell how we are going to select the pivot. But suppose that the pivot is chosen randomly to be any item in S. with equal chance. Okay, so we can pick any item of S to become the pivot. Then, with high probability, the running time is theta of n log n. So let's say 95% of the chance the running time is n log n, and on average it is of n log n. Now, Quicksort makes use of a step called partition, where we are using the pivot P to partition the set S into two groups, one smaller, one larger. Now, in the actual implementation, the set S may be stored in a certain array A. So if we want to do the partition step, after the partition, it would be nice so that we are using the array A to store the result so that S small will appear in the left part of A, S large will appear in the right part of A so that P stays in the middle. Now, if this is the case, then P will be in the correct position of A if A is ever going to store the sorted result. So what remains to do here is we are going to do the sorting of S small recursively and the sorting of S large recursively. So in the end, A will become the sorted S. So here, the original numbers are stored in contiguous position in an array, and after the partition step, we hope that P will stay here so that the left part contains the S small and the right part contains S large. So this is the partition step. Now, the partition step can be done by using an extra array, let's call it B, to help us. So how do we do the partition? So we get S, we get an item P. So what we can do, okay. So we are going to look at the items of S one by one. Now, if it is smaller than P, then good. Then we put it to the left part of A. But when the item that we see is larger than P, then we will put it to B temporarily. And after all the numbers are processed, we are going to copy the numbers that we store at B temporarily back to A. So we are going to put them to the right part of A. And then we also put P to the correct location. So in this case, we can see that we can perform the partition step as we want, with this extra array B to help us. But the question here is that, is this extra array B necessary? So can we perform everything so that without creating such an extra array? So here we are going to show this actually can be done. We actually do not need this extra array B. First of all, without loss of generality, we assume that the pivot P is the rightmost item of A. If it is not, then it's easy. So we take a pivot and then swap it with the rightmost item of A so that we put this pivot intentionally at the rightmost end of A to begin with. Okay, now the idea of the partition step is we are going to move the smaller items to the left part of A. But then we are going to look at the items of S one by one and then move the smaller items to the left part. But doing so, we also keep track of the location that we are going to store the next smaller item. Okay, so we will see an example soon. Then what we are going to do here is that when we hit the smaller item, we swap it with the original item at location Z, which is the position that we try to store the next smaller item and update Z. But when we hit the larger item, we will just ignore it. So it looks like, you may not know what I'm talking, but it is actually a simple method. So we will see the example run. So what we are going to do here is that, okay, so let's see, this is the array for storing the original numbers. 5 is the pivot, and then we want to do the partition based on this pivot 5. So we are going to scan all the items from left to right in this array, processing it one by one. This is the current item that we see, and Z points to the location where if we discover certain items that is smaller than the pivot, we will put it here because we want to put the items that are smaller than the pivot to the left hand side. Okay, now at step 1, we look at this one, and then we find that this one is smaller than this pivot, so we are going to put 1 here. 1 is now put, this is the old Z. So once we have used this position to store a smaller item, then in that case, we will update Z so that it points to the next location. So whenever we have another smaller item, we are going to put at this location. Now, as we can see, at this moment, we are looking at this item 3, and 3 is smaller than 5. So we are going to put 3 at this location and update Z. So this is what we see after one step. After this step, then we are going to look at this 7. Now 7 is larger than 5. Then what we are going to do? 7 is larger than 5, so we are not putting any number here. But on the other hand, this Z is still pointing at this location because this is where the next smaller item should be placed. So when we process this number 7, what we are going to do here is we just move the current element 1 position rightward. So we will ignore the 7. Okay, we move it. And now we look at this 8. 8 is greater than 5, so again, we will ignore this 8. And after that, we will see this 2, right? Now when we see this 2, what we are going to do, okay, 2 is smaller than the pivot, so 2 shall be moved to this position. That is what we are going to store this number. And then when 2 will be now swapped with this one. So after this step, 2 will be placed here, Z will be updated. So this is what we are going to do after this step. So 2 is now here, Z is now updated. And then after that, we continue to look at the next item, which is 6. 6 is greater than 5, so we ignore it. And after that, we look at this 4. And then again, this 4 will be smaller than 5. So 4 is going to swap with this 8. And now Z will be updated. So this is what we are going to do. And finally, we get this 5. 5 is the last item, and this is the pivot. So we are going to swap this 5 with what Z was pointing. So because this is going to be the end of the smaller item part. So we are swapping this, and then this is done. So in this case, we see that everything, okay, in this step are done on the same array A, and we do not need to use an extra array B to help. Now this method, or this kind of algorithm that doesn't use extra memory to help, is called in-place algorithm. So for sorting, so that we have studied so far, then we will see that insertion sort or bubble sort, they are both in place. On the other hand, if we use extra space to help in performing an algorithm, then the algorithm is called out of place. For instance, merge sort normally is an out of place algorithm because the merging step often requires an extra array to perform efficiently. Okay, so this is the end of this lecture. Thank you.